Okay, welcome to the EOL seminar. Today's speaker is Willem Marais, and he grew up in South Africa and went to university there, to the University of Pretoria, and did his bachelor's there. And then he came to the US and did his master's and PhD degrees at the University of Wisconsin-Madison in the Electrical and Computer Engineering department. So Willem has stayed at the University of Wisconsin since then. He was first a postdoc, and he's now a scientist there. And his expertise is the denoising of all kinds of lidar data. And here at EOL RSF, we actually use quite a bit of his work. So we denoise our high spectral resolution radar data with his denoising processing codes. He's currently here to work on our micropulse style data with Matt Heyman and Scott Spuler and Tammy and all of the others of the MPD team. But today we are going to hear about CALIOP images, and so we'll hear more what that is.
Thank you. I'm going to present to you work that I've been doing with my collaborators, Robert Holtz, that's at SECC, and Rebecca Willett, who's used to be my advisor, now we're collaborators, so that's the University of Chicago, and Chip Trepty, that's at Langley Nassan, who's funding us in our effort to develop methodologies to denoise satellite-based lidar instrument data like CALIOP. What you see in this slide to the far left is a simulated space-based, well, not exactly space-based, but a simulated lidar observations, where the SNR is very similar to that of a space-based lidar instrument, and the noise is the same as that of CALIOP. So you can see there are cirrus clouds in this. There are cirrus clouds you can almost see, and a small aerosol layer. The methodology we developed retrieved the attenuated backscatter coefficient from these noisy observations. And like Matt mentioned, is that Ed Eloranta once looked at my work and he said, well, this is a snake oil, that can't be true. And I think he's convinced by now that what we are doing is true. So I'm going to try to convince you through the presentation that this result of inferring the attenuated backscatter coefficient of the cirrus clouds and the aerosol layer is legit. And how I'm going to convince you is that I'm going to tell you the basic components that our methodology relies on, and it's based on sound theory. Then I can explain to you I can give you a little bit more detail about the noise that CALIOP has to deal with. That's different from the noise that Scott Spuler and Matt has to deal with their MPD system or HSRL. And then I'm going to explain to you how we create realistic simulations with which we can quantify the performance of our methodology. Then I'll share the results with you. Like Scott asked, if it is a real CALIOP scene, and it's not a real CALIOP scene. As of now, I was not able to get access to raw CALIOP data because of my status in the United States, and I recently became a permanent resident. So I will be able to get access to CALIOP data in the future, and then I can apply my methodologies on it. So for those who don't know what CALIOP is a space-based lidar instrument that was launched in, I think, 2006. It's what we call a standard backscatter lidar that makes measurements at 532 nanometers and 1064 nanometers. And in order for you to retrieve the extinction coefficient, let's say of aerosols or clouds, you have to assume what we call a lidar ratio or a backscatter phase function. The reason why I show you this image, it's a daytime 532 nanometer channel image of just south of Oman. And what you can notice in this image is very grainy. Even though you see the clouds, the water clouds, and the desert dust, it's very grainy. That's because of the photon detector noise. And because of the cumuliform clouds that's near the planetary boundary layer, they reflect a lot of sunlight towards the lidar instrument. So you have this extra noise just above the clouds. So if you want to retrieve the extinction coefficient of, let's say, the desert dust or clouds, depending on how tenuous they are, in order to increase the SNR of the measurements to get meaningful results, sometimes you have to average the data from a horizontal resolution of 1/3 of a kilometer down to either 5 kilometers or sometimes up to 80 kilometers for desert dust or for smoke or any kind of aerosols. So that's a problem because if you could, as you can see in the slide, the desert dust, as we can see here, is highly non-uniform. So if you're going to do 80-kilometer averaging on the scene to retrieve the extinction coefficient of, let's say, this aerosols, you can induce biases because of the non-uniformity of the aerosols. On top of the biases that you're going to have by assuming a lidar ratio. And if there's any undetected clouds within this aerosol layer because of the excessive noise, if those clouds are undetected and you're going to average over those to retrieve the extinction coefficient of the aerosols, you can have extra biases. And that motivates us to find different methodologies to not do averaging to reduce the noise.
Question. It collects data. Does it collect optical depth? It's only backscatter.
And in the backscatter for which you...
HSRL, we do collect both optical depth and backscatter. How is that different? That looks like you are just doing backscatter only.
Yes, so okay, thank you for asking that question. CALIOP only measures the standard backscatter both due to molecules and aerosols. So you use the single scatter lidar equation with an assumed backscatter phase function to retrieve the optical depth. With the HSRL, you don't have to assume a lidar ratio.
You got one more process step. Okay.
Yeah, and by assuming a lidar ratio, if you have to guess what the lidar ratio is, and how they do it is they look at the depolarization of the clouds or aerosols to know whether it's dust or clouds. And that helps you decide what the lidar ratio is. But guessing an incorrect lidar ratio bias your results for retrieving the extinction coefficient or the optical depth. But on top of assuming a lidar ratio, if you're going to average the data, because of the non-conforming unity of the scenes, you can induce extra biases. Any other questions? So that motivates our work for developing methodologies to reduce the noise, so you don't have to average the data in order to retrieve the optical depth of clouds or aerosols or getting the extinction coefficient. So how we do it, we rely on the basic concepts or ideas that's supported by theory. And this, I can explain it to you with a little bit of mathematics. Is that, let's say you have a parameter that you want to infer, which let's say is that unit backscatter coefficient, and I label it via x. We have a forward model that tells us what we expect to get back of the scattering. And that's what we use the single scatter lidar equation to model the backscattering of the atmosphere based on the laser pulses we transmit through the atmosphere. And that's what I call f of x. Then we have our noisy observations, and we assume that the expectation of the noisy observation is approximately equal to the single scatter lidar equation that's parameterized of the true image that we're trying to infer. Now, like we do with the MPD system and what Matt Heisman has been doing with the HSRL, if you have a phone counting lidar instrument, and it the same holds for CALIOP, if you know what your noise is, then if you can describe your noise and you can define a well-defined noise model, you can use that noise model to help you estimate the parameters you want. What the noise model allows you to do is that if you have an estimate of your attenuated backscatter coefficient and you plug it into your single scatter lidar equation, you can see how you can quantify how close of a fit your single scatter lidar equation is relative to the noisy observations. So in other words, if your attenuated backscatter coefficient is totally incorrect, the noise model will tell you, it will give you a large quantity telling you you're totally incorrect in guessing or estimating the attenuated backscatter coefficient. So that's the one component we need as a noise model. So while we estimate the attenuated backscatter coefficient and fitting into the noisy observations using the noise model, we could strain our estimation by imposing an image structure using what we call a regularizer term. And that helps us. So, but I forget to mention, this is what I want to point out in the previous image. The reason why we impose a structure is that we need to make a distinction between the noise that's random and the atmosphere that's non-random. And that's what we can do with the formulation that I showed you in the previous slide, is that you estimate your signal by saying, I know the clouds and the aerosols have a structure that's distinct from the randomness of the noise. And that's how I infer my extinction or my attenuated backscatter coefficient. So let me explain a little bit about the noise and why it's important to have an accurate noise model. So like with the MPD and similar to CALIOP, because we found in counting the noise is Poisson distributed, the noise variance is equal to the mean, meaning what we assume to be the single scatter lidar equation when you do your estimation. So if you have very low photon counts, your noise variance is relatively large compared to your mean, your single scatter lidar equation, meaning that the SNR is very low. And what the Poisson noise model also helps you with is that it models the fact that your observations are non-negative. If you were to assume a Gaussian distribution as your error model, then it doesn't model for you that your observations are non-negative. The Gaussian noise model tells you that the noise can be negative, which is not true for photon counting observations or with CALIOP. And that's one of the reasons why an accurate noise model is important. In the next two slides, I'm going to explain to you what I mean by imposing an image structure to constrain the estimation of the attenuated backscatter coefficient. This is an example of where we say, okay, let's assume that the image we want to estimate can be accurately approximated with piecewise constant functions. One way of doing that is to saying, my regularized term is the summation of the absolute values of the discrete derivative of the signal you're trying to estimate. Depending on how much weight you put in as a regularizer, what it does, it promotes that your discrete derivative have more 0 points versus compared to the points that are non-zero. So in other words, in signal processing, what we say is that we induce sparsity on a discrete derivative of the signal we're trying to estimate. And that's what we do with the MPD instrument when we estimate the water vapor with the methodology that me and Matt is developing. So here's a noisy image of a block wave that's noisy, and it's showing the cross-section with these two plots. The blue curve shows the noisy observations. The green dashed curve shows you the true signal that was estimated, and the orange curve shows the signal that was estimated, assuming the signal you have can be accurately approximated with a piecewise constant function. And here's the image structure that was imposed by saying the discrete derivative of the signal has to have a lot of zero impulses with a couple of non-zero impulses. So that's one way of inducing an image structure. Another way of imposing an image structure is by exploiting a redundancy in an image using non-local means estimation. So how you exploit redundancy in the image is that if you divide the image into small little patches, and if you group those patches based on the similarity, they have redundancy among each other. And that's how I illustrated this in the slide, that idea. Here's a picture of a noisy house. The image was divided into little patches, and the patches that were aligned towards the roof, because they're very similar to each other, they were grouped together, as you can see in this part of the slide. And because they have a lot of similarity, they look very similar to one another, they share redundancy, you can exploit the redundancy to remove the noise via principal component analysis by looking at a small subspace, or you can use wavelet denoising, or you can use averaging. That's the way you remove the noise. One of the ways you remove the noise from the patches. And once you have your denoised patches, you can reconstruct your original image. So that's the methodology is called non-local means estimation. In order for this methodology to work, like I said, if you compare the patches to one another, you need to measure the similarity between them using, let's say, the including norm. But in order for that including norm to give you accurate information to say whether the patches are similar to each other, the SNR of your signal has to be high enough. Now, for very low photon counting observations, your SNR is very low, so it's difficult to measure that similarity. So in this slide, I show you the USA flag that was flipped with that's corrupted with Poisson noise. I think the photon rate was 1. As you can see, the SNR is very low. So if you're going to do the non-local means estimation on it, if you can compare patches with one another, it's going to be inaccurate. So what makes Poisson noise, or the noise that CALIOP has, unique is that if you reduce your image resolution by binning the photons together, you increase the SNR, but you're sacrificing resolution. And that's what I show in this slide. So if you have a coarser resolution, and you reduce the resolution again, and you have a very coarse resolution, the SNR increases. So the basic idea of a methodology that me and Rebecca Willett developed called ProxBeam 3D, that's based on another methodology that was just for denoising, and what we developed was for inversing, is that we start with a very coarse resolution for an incoming image. We try to infer the image from this coarse resolution image. And then we say, okay, we have a fairly accurate estimate of the image at a coarse resolution. Let's use it as an initial condition, as an initial estimate, for inferring the parameter for the coarser resolution, a little bit higher resolution. And that helps us to get an accurate estimate of this coarser resolution image. And then we go to a higher resolution image. It's noisier, but we have an initial condition, initial estimate that's accurate based on the previous image resolution. And we go all the way down to the original image resolution. So to demonstrate the effectiveness of this methodology, as what we published in a conference paper, here's an image of a bridge, which is a normal photograph, where it was corrupted with Poisson noise with missing data. So we have a Poisson noise model that tells us the properties of the noise. We have a forward model that tells us where the missing pixels are. And then we can use either total variation inference, where you promote a piecewise constant function. You say that the image that I'm trying to estimate can be accurately approximated with a piecewise constant function. This is the result you will get. And if you use the ProxBeam 3D method, using the non-local means estimation methodology, this is the result you get. The reason, so non-local means estimation doesn't constrain the signal that you're trying to estimate to be piecewise constant. It allows more detail to be estimated compared to approximating your image with piecewise constant functions. So even though this methodology, ProxBeam 3D, has a high performance compared to total variation inference or denoising, it comes with restrictions. To get a little bit technical, the objective function that you're trying to minimize with total variation inference is well defined, and if you minimize it, then you know whether you reached either a local minimum or a global minimum. With ProxBeam 3D, you don't have an explicit form for the objective function. In other words, you don't know what the function is you're trying to minimize, and that's the problem with ProxBeam 3D. I can give you more detail what the distinctions are in a slide that I put way at the back. Let me explain a little bit about the noise that CALIOP deals with. So how CALIOP measures the energy that's scattered back towards the instrument is that they don't count the photons that's detected by the PMT. They measure the current output, literally the current output of the PMT. And the noise model that describes that current output, if you measure it continuously, is compounded Poisson. And the reason why it's compounded Poisson is that if you have a PMT and it's inside the PMT there are dinodes, the photocathode is struck by photons. It's a Poisson process that describes the output of the photocathode. Then you have a dynode that amplifies the photons of the photocathode. That induces another Poisson process. And the next dynode induces another Poisson process. So you have this cascading effect where each dynode imposes a different Poisson process. And you end up with a Poisson process and a Poisson process and a Poisson process. And that's why it's called the compounded Poisson process. So for a photon rate of 1 per second, this is how the probability distribution or the histogram looks like for the PMT. And it's distinct from the Poisson property mass function because you have this little impulse that indicates there's a very high probability you will get a lot of zero photon electrons coming out of the PMT. So the model that describes the compounded Poisson noise, you can write it down as a mathematical function, but it's not analytical. It's not like with Poisson noise that it's a closed form expression. Compounded Poisson noise is a summation within a summation within a summation without an explicit formulation. So you can't really use it as a noise model analytically. So we have to come up with an approximation for the compounded Poisson noise. So how we do it is, what I've noticed is that if you normalize your output of your PMT with the gain of the PMT because it amplifies the signal. The noise model that you get with the normalized PMT values, output values, can be approximated with a Poisson probability mass function or Poisson noise model. And so that's what we do, is that we take the measurements that comes out of the PMT, we normalize it with the gain of the PMT, and we approximate the normalized values with the Poisson noise model. So that's an approximation that we do. And even though it's an approximation, we are still able to accurately infer the T-net backscatter coefficient from the measurements. Now, I'm going to switch gears and explain to you how we create simulations with which we can then quantify the performance of our methodology. And since I don't have access to I haven't had yet access to raw CALIOP data, I had to simulate data myself. And so what we do is we say, okay, Edeloranta has a very beautiful lidar instrument at Madison, Wisconsin that makes high SNR measurements of the atmosphere. So let's use this instrument to generate data for us. So here's an example of what the HSRL at Madison, Wisconsin produce. And what we do is, okay, Edeloranta makes high SNR measurements of the atmosphere. Let's reduce the temporal and the spatial resolution of the image so that the spatial and temporal resolution is similar to that of a space-based lidar instrument. In other words, that the horizontal resolution of the image is similar to CALIOP, which is 1/3 of a kilometer. So that's the first step of what we do, reduce the spatial and temporal resolution. Next step is to reduce the SNR of the image so that the SNR of the image is similar to a space-based lidar instrument. And we use a technique that we also use with the MPD. It's called Poisson thinning. And basically what it does is that for each pixel in your photo counting image, you, with a random process, you randomly sample the individual photon counts, and the photon counts that you sampled, you place in a second image. And depending on what type of random sampling you use, your second image is also Poisson distributed, but it has less photon counts, therefore its SNR is lower. So with a high SNR image, we can create a low SNR image, where the SNR is similar to a space-based lidar instrument. Then, as an extra step to make it further, make the noise increase the noise, to make the SNR much more lower, is that we can add Poisson random variables to each column. And then we end up with a daytime simulated low SNR lidar image.
What's the low and high SNR in your definition?
Meaning that the noise variance is increased, well, the noise variance increases relative to the mean.
Yeah, is that 10 dB or 0 dB? What is that?
I'm not a radar expert, so we don't normally work with dB. I'll share in a couple of slides how I define it. So now if we allow SNR image, we have high solar background radiation. Even though we use the ground-based lidar instrument to make the simulation, meaning it's up-looking, not down-looking, it's still valuable for us to use this data set to evaluate the performance of our methodology. So let me move to the results. Here's a simulated scene where the horizontal resolution is similar to what a space-based lidar instrument will see, like CALIOP. And you can see this all these vertical stripes, which is the solar background radiation, and there's a little bit of a cirrus cloud that's sticking out, and a little bit of an aerosol layer sticking out. And this is the high solar image from which we made the simulation. So to answer your question about SNR, how I how I envision SNR, as I say, okay, if I were to average all the columns in this image and subtract the background, I will get this blue curve. My background signal is this large. So when I say it's low SNR, I say the background signal is much larger than the signal they're trying to estimate. So around about 8 kilometers altitude, the backscatter is such that the photon counts you will get due to molecular scattering will be between 1 and 2 per second. And in this graph, I show you the high SNR data set from which the low SNR data set was created. In this result, I show you, okay, this is what you saw in the first slide, the introduction slide. This is if you don't do any averaging, this is what you will get if you want to infer the attenuated backscatter coefficient. This is what you will get if you infer the attenuated backscatter coefficient with the Prox-beam 3D methodology that we developed, adapted for CALIOP. And this is the truth, in quotes, which is actually the highest in our attenuated backscatter coefficient. So we were able to retrieve the aerosol layer, the cirrus clouds, though there's a couple of things we didn't retrieve. For example, this little blip of a cirrus cloud we didn't fully retrieve. So there's still improvements that we can make, but so far so good. If we reduce the resolution of the noisy image from 1/3 of a kilometer to 5 kilometers, this is how the result would look like. The SNR has been increased, but there's still a lot of residual noise. But you were able to retrieve some of the aerosol layer in the cirrus clouds. I'm going to quantify the results for you by taking individual profiles and plotting the profiles for you. So you can see how they compare quantitatively. So the blue curve is the standard method, meaning that for 5 kilometer resolution, so where the standard method is where you just did averaging to get a attenuated backscatter coefficient. The black curve is the high SNR measurements of the attenuated backscatter coefficient. The orange curve shows the attenuated backscatter coefficient of the new methodology we developed. And as you can see, there's less residual noise for the new methodology. There's a slight bias for retrieving the attenuated backscatter coefficient for the cirrus cloud, even though for the aerosols we have less bias with less residual noise. So far so good. The only problem is with our methodology is that we might have a slight bias for the molecular backscatter way up in the atmosphere, and it has something to do with the initial condition that we used in our estimation procedure, which can be improved upon. I'm going to share another profile, where the profile is now specifically at this aerosol layer that has a high backscatter. And because we did averaging with the standard method, it underbiases the attenuated backscatter coefficient for the aerosol layer, where with the new methodology, the attenuated backscatter coefficient is not, it has very low bias, almost visibly no bias. And we are able to somewhat retrieve a very tenuous aerosol cloud, cirrus cloud. And again, there's bias in the upper layer of the atmosphere that we will need to fix, and I think I have a couple of ideas how to fix it. Just to further quantify the errors, what I've done is I identified the specific features, like this upper layer cirrus cloud, lower cirrus cloud layers, and the aerosol layers. And what I've done is I computed the root mean square error for the attenuated backscatter coefficient for all these cloud layers. So with the standard method, where the horizontal resolution is 5 kilometers, the root mean square error is like 0.5. For the high altitude cirrus cloud, with the new methodology is 0.15. Now, what you expect is that if you're going to do more averaging, because the aerosol layer is very uniform, you should get lower root mean square errors for the aerosol layers with more averaging. So if you do 80 kilometer averaging, meaning that you average the whole scene together to get the attenuated backscatter coefficient for the aerosols, your error does decrease, but it's not as low as with the new methodology that we developed. So just to conclude my presentation is that, so with the methodology we developed, and hopefully I will get raw data soon, the hope is that we can then retrieve the attenuated backscatter coefficient and hopefully the extinction coefficient, even though you have to assume a large ratio, for the 10-year data record of CALIOP, which will be valuable for the scientific community. All the results I've shown you is inferring the attenuated backscatter coefficient from the parallel polarized 532 nanometer channel. I'm busy testing my methodology on perpendicular cross-polarization measurements. Our next step is to, once we get the raw data from Langley, we can apply the methodology to several granules of CALIOP data and generate statistics to show the validity of our methodology. And currently the methodology is slow. It's something we have to improve upon, usually, hopefully with GPUs. The other point that we want to make through our work is that we hope that the methodologies that we develop will be applicable for future space-based lidar instruments. And we hope that we can explore the idea of how signal processing methods like we developed can help improve the design of lidar instruments. Like how can you make a compromise between software and lidar and hardware when you design a lidar instrument in order to do measurements. So I also showed you how to retrieve the extinction, the attenuated backscatter coefficient. I need to refine the methodology so you can infer the extinction coefficient using assumed lidar ratios. So you don't have to, not just retrieve the attenuated backscatter coefficient, but directly estimate the extinction coefficient. And that concludes my presentation. Is there any questions?
Yeah, maybe I missed it, but your third last bullet point there with accurately model the noise.
Yes, sorry.
You ended up with a Poisson process, but I didn't quite understand if this was because noise in general follows a Poisson process, or if it was by analysis of your image that you got that.
So you're right. I mentioned a lot of times Poisson noise, and it's very subtle when I went into compounded Poisson noise. So CALIOP have compounded Poisson noise, and so we acknowledge that, and we approximated Poisson noise as Poisson noise by appropriately scaling the observations. So what ends up happening is that if you scale the output of the PMT, the error function that you derive from the noise model for compounded noise is very similar to the Poisson error function. But all the results you saw for the simulated CALIOP is all compounded Poisson noise.
Other questions?
For the HSRL, how different is the noise model? Is that the same as it's different?
For what Matt Heyman and Scott Spuler have, they have a phonic counting system, so the noise is Poisson, which is well defined, which is different from this.
Oh, it's not compound Poisson. See Poisson, you said that's a different Poisson.
Yeah, this is compounded Poisson that's the noise for CALIOP.
Okay, this is the Poisson just by itself.
Yeah.
Other questions?
Hi, Mike.
So are you applying that methodology where you look for the little patches and use that to characterize the image first?
Yeah.
And when you do that, are you doing it uniformly everywhere or in layers? Or I mean,
That's a
do
very
you
good
have
question.
a sort of way of predicting which one is where more of the information is going to be?
So the method that we use was developed by researchers in Finland. It's called block matching 3D. There's the algorithm that we depend on. And what they do is, so each patch is 8 pixels by 8 pixels. So in our case, it will be 303 meters and 15, well, a third of a kilometer times 8 and 15 meters times 8. And what then they do is they say, okay, in order for me to look for patches that are very similar to each other, let's restrict my search window to be 40 pixels by 40 pixels. So you look over a 40 pixel by 40 pixel block and not the whole image. Does that make sense?
Yeah, and then you move and then you go to another 40
Yeah.
pixel.
Yeah, for each patch that you want to denoise, your search window changes.
So I guess if I use this example, I can visually see you get more organized structure there. But if you look at original noisy one, so if I look at the right one, can you tell whether certain information is less certain than? Can I assume those more organized things actually the more robust measurement, or can you quantify this retrieved information? Like, for example, if I want to do data simulation, I actually do need to know error statistic. So it's for your right one, is that all the signal is equally good, or can you quantify, say, well, some are less certain, maybe I should be more careful how I interpret results?
So just to understand your question, can we quantify the uncertainty of?
Yeah, like this signal, this structure, maybe more organized structure, maybe something measurement see quite clearly, and that's you feel that's fairly robust measurement. And the others actually can't find, you denoise whatever, and do they means they're certain, or are they equally good?
Okay, so if you, so you're asking, just to sure if I understand your question, if I'm going to denoise this image using patch-based denoising, so if I'm going to have several patches and measure the similarity, how certain am I that they're very similar to each other? Is that getting close to your question?
You were talking about like in the context of data assimilation?
Yeah.
So you need to know the uncertainty of your observation that you're assimilating. Otherwise, you might force the model to agree with noise.
Okay.
It's more a question of like, do you have a metric for measuring the uncertainty in your retrieval?
The overall retrieval. Oh, okay, now I get it. I can't use traditional methodologies to quantify what uncertainty is using standard error propagation because the methodology we have is very highly nonlinear. But what we maybe can do is that we can numerically compute what the uncertainty is using cross-validation methodologies. So we do it iteratively numerically. That's one way of doing it. But I don't have this so far no analytical way of doing it.
There are other questions? Actually, I have a question. You said currently your algorithm is still running slow. Can you quantify that? I mean, for example, how long would it take to run this image?
So, like I said, we start with a coarse resolution, and then we do the estimation at finer resolution and a finer resolution to the finest resolution. So to denoise a CALIOP image that looks like this, doesn't look like this, but if this was a CALIOP image, it will take 4 hours to infer the extinction after the Attenuated backscatter coefficient, then 4 hours again at the next coarser, finer resolution, and again 4 hours at the finer resolution. So depending on how many levels you have, it's that times 4. So it's very slow. But there's potential that you can increase the computational, decrease the computational time with GPUs. It's something that we have to look into. I was waiting for a question from Matt.
It's an easy one. So, I mean, most of what I'm familiar with is, in working with you, is we're working with Poisson or similar compounded Poisson noise. But what about like Gaussian noise? Can you apply total variation or block matching 3D with a Gaussian noise model or just any arbitrary noise model? You just need to know it.
If you have a mathematical tractable model for it, yes.
And can you do Gaussian thinning? Does that work?
No, there's other methodologies for dealing with Gaussian noise, and that's actually the Poisson thinning technique doesn't work on compounded Poisson noise. So what you do instead is that you take your image and you withhold random pixels from the image, and you put it in the second image. Then you say, okay, I'm going to denoise my image and then interpolate and also estimate the missing pixels. And then you compare it to the image that has the pixels that you withheld. And then with that, you can quantify an error to say how accurately did you estimate the image. And that's what you would do with Gaussian noise. One way of doing it. With Gaussian noise, if you know the standard deviation of your noise, then you don't have to do it.
Well, if there are no more questions, then let's thank Willem again.
Thank you.